All right, so let's get started. Today, we're going to talk about covalent bonds, but this is a great example or analogy. A plant absorbs water through the roots from the soil from a solution containing nutrients. Carbon dioxide in the air enters into the plants through small openings in their leaves. It's like the plants breathe, right? And the plants use the energy from the sunlight to convert the water and carbon dioxide into sugar. So what does this have to do with covalent bonds? How are atoms held together in a covalent bond? Well, the attractions between the shared electrons and protons in the nucleus hold the atoms together in a covalent bond. A covalent bond is a chemical bond in which two atoms share a pair of valence electrons. So yesterday we talked about ionic bonds where one atom's like, hey, you can have my electron. Covalent bond is like, hey, do you want to share an electron? So, but as you'll find out, some of these bonds, they share it's like the electron is a child and their parents are divorced and they're shared and there's a schedule. Some of these molecular covalent bonds, the electrons will spend more time with one atom than the other, but they are shared. So sharing electrons, a hydrogen atom has one electron, one valence, well, it has one electron period, but it's one valence electron. And if it had two electrons, it would have the same electron configuration as helium. Okay? Two hydrogen atoms can achieve a stable electron configuration by sharing electrons and forming a covalent bond. So where we're going with this is that hydrogen is diatomic. It likes to be stable just like helium does. It wants two electrons in that first energy shield, or energy ring, the ring like when we talk about our diagrams. So usually hydrogen travels in pairs. Usually there's two hydrogens together always. There are several ways to show a covalent bond. In the electron dot model, the bond is shown by a pair of dots in the space between the symbols for the hydrogen atoms. In a structural formula, the pair of dots is replaced by a line. The electron cloud and the space-filling model show the orbitals of the atoms overlap when it's a covalent bond. So here's an example of that. This is the electron dot. Now remember yesterday, and it may not pop up right in your head because you only saw it one time yesterday, but when we did the electron dot diagram, there was only one dot for hydrogen because there's one valence electron in hydrogen. Well, this hydrogen has one valence electron, and they share those. And that gives them both two, which is what they want for that first energy ring. Now, another way to write it is what we call a structural formula. Instead of using the dots, we use a straight line to represent the sharing of those two electrons. This is a space-filling model. This is important like when we're trying to diagram or show somebody a three-dimensional model of what the molecule kind of looks like. And this is the electron cloud model. It's showing where the electrons kind of live. The overlap indicates that they're sharing an electron or two, okay? So an illustration of this or an analogy is as the space shuttle lifts off, it leaves a water vapor trail. A reaction of hydrogen and oxygen produces water. I think they burn liquid hydrogen. That's why it's so explosive. And whenever you burn something, it combines with oxygen. Okay? Does that make sense? Okay. And so one of the byproducts is water. So molecules of elements, and that's not really an analogy. I don't know why they showed that, to be honest with you. I think it's because they burn hydrogen. So when they burn the hydrogen, these two hydrogen atoms will form a bond with the oxygen and leave a water vapor. Two hydrogen atoms bonded together form a unit called a molecule. A molecule is a neutral group of atoms that are joined together by one or more covalent bonds. So a hydrogen molecule is neutral because it contains two protons and it contains two neutrons. Or not neutrons, two electrons. A chemical formula can be written as H sub 2. right? So the fancy word for these molecules that are really atoms or elements are called diatomic. Di means two. So these are diatomic. In other words, they travel in pairs. So fluorine, F2, is diatomic. Nitrogen is diatomic. Chlorine is diatomic. Bromine is diatomic. Iodine is, and this is group 17. So they have 7 valence electrons, and they share 1 with each other, so they kind of have 8, okay? There's lots of diatomic atoms. Oxygen is one. Anyways, that's why when you watch a medical show, they say, give them O2. You ever heard them say that before on a medical show? Give them some O2. They're talking about oxygen, really. Anyways, it says when an ozone is O3. What? Anyways, when 2 atoms share 3 pairs of electrons, the bond is called a triple bond. When 2 atoms share 2 pairs of electrons, it's called a double bond. Nitrogen has 5 valence electrons. Did I say they were group 7? These are, no, so the chlorine, bromine, and iodine are group 7. Fluorine is group 7. Nitrogen kind of snuck its way in there. That's a group 5. But anyways, nitrogen has 5 valence electrons. How does it get 8? Well, it needs 3. So they kind of share 3 each. So when an atom of nitrogen, or a molecule, N2, share 3 pairs of electrons, each atom has 8 valence electrons. Each pair of shared electrons is represented by a long dash. So the way that we would write that in a structural formula is N, 3 dashed lines, N. Okay? Now, when I look at that, I go, there's a triple covalent bond between the 2 nitrogen atoms. What happens when atoms don't share electrons equally? What factors determine whether a molecule is polar? So, when atoms form a polar covalent bond, the atom with the greater attraction for the electrons has a partial negative charge, and the other atom has a partial positive charge. And a lot of this has to do with the size of the atom itself. So remember that these electrons have to be shared. There's a greater attraction. Think of gravity if you want. A more massive object has a greater gravitational pull than a smaller one. Earth pulls on the moon far more than the moon pulls on Earth. Does that make sense? Okay. So then a second type of atom, or the second type of atoms in a molecule, and its shape and factors determine whether it's polar or nonpolar. So if you have 2 molecules that are very similar in mass, or the amount of time that they share the electron is a better way to word that, that would be what we call a nonpolar covalent bond. So except for the noble gases, that's group 18, right? Helium, neon, argon, all those. Elements to the right of the periodic table have a greater attractions for the electrons than the elements on the left, right? So the metals, group 1, they only have like 1 valence electron, right? So they're going to have that tendency, just like yesterday when we talked about ionic bonds, they're going to have the tendency to want to loan their electrons out to the other atoms. And so if you're a higher group number, you're going to have a greater attraction, okay? So elements at the top tend to have a greater attraction for electrons than elements at the bottom. And this just really has to do with the structure. So polar covalent bonds, in a molecule of an element, the atoms that form covalent bonds have the same ability to attract an electron. Shared electrons are attracted equally to the nuclei of both atoms. In a molecule of a compound, electrons may not be shared unequally. So a covalent bond or a covalent compound forms when hydrogen reacts with chlorine. The chlorine atom has a greater attraction for the electrons than the hydrogen, right? Chlorine's group 17, hydrogen's group 1. The covalent bond and the electrons are not shared equally, so it's a polar covalent bond. So if we were to draw this in the electron cloud, right, you could see that the shared electrons of the hydrogen chloride molecule spend less time near the hydrogen than they do near the chlorine atom. Can you assume that the molecule that contains a polar covalent bond is polar? When a molecule has only 2 atoms, it will be polar. Okay? When molecules have more than 2 atoms, the answer is not obvious. So like glucose, sugar, there's a lot of atoms in each molecule, and it looks a certain way. And then more complex organic materials, like proteins and stuff, you can't make those predictions, but it's real easy. Generally, just like the ionic bonds, you have a non-metal that tends to want to link up with a metal, group 1 versus group 7. They want 8 electrons in the outer ring, unless it's hydrogen or helium. They can only hold 2. And that's where the sharing takes place. Okay? In a covalent bond, because they're sharing, the larger molecule has a tendency to have a greater attraction to the electron than the smaller molecule. So it's usually polar if it's just 2 molecules. If it's diatomic, then it's not necessarily polar. So let's look at carbon dioxide. So carbon dioxide, as a molecule, it's got 1 carbon in the middle and then 2 oxygen on the opposite sides. The polar bonds between the carbon atom and the oxygen atoms cancel out because the molecule is linear. Okay? But now if you look at like water has a polar bond and it's not linear. The shape is different. Does that make sense? So the molecule looks like it's bent. In carbon dioxide, there are double bonds between the oxygen atom and the central carbon atom. So carbon has 4 valence electrons. It's in group 14. Oxygen has 6 valence electrons, right? So that is in group 16. And they have to have some double bonds and stuff because oxygen needs 2. And carbon technically needs 4. So that's why there's 2 oxygen per 1 carbon. So the carbon will share 2 electrons with the oxygen to kind of fulfill oxygen's needs, but it'll share it with another oxygen atom, so that way carbon can have 8 as well. Okay, so there are some pulls because of the charges. The electrons are on opposite sides, so they cancel each other out. That's what they're saying. In a water molecule, there are 2 single bonds between the oxygen and the hydrogen. So these bonds are polar because oxygen has the greater attraction. This is literally what the molecules look like. Okay? Those electrons in the H2O spend more time with the oxygen than they do with the hydrogen, so the charge is different. Now, if you take the next level chemistry class, it'll explain why the charges are different and where the charge is located, and that determines the placement of these 2 hydrogen molecules. Because this is linear, there's a charge here, there's a charge here, and those charges, those attractions cancel out because they're on opposite sides. How do attractions between polar molecules compare to attractions in nonpolar molecules? And basically, attractions between polar molecules are stronger than the attractions between nonpolar molecules. So in a molecular compound, there are forces of attraction between molecules. These attractions are not as strong chemical bonds, but they are strong enough to hold the molecules together in a liquid or a solid. Water molecules have are similar in mass to methane, which is carbon H4. Yet methane boils at negative 161 degrees Celsius and water boils at 100 degrees Celsius because the methane molecules are nonpolar and water molecules are polar. Okay? So dashed lines represent the attractions between partially positive hydrogen atoms and partially negative oxygen atoms. These symbols are delta minus and delta plus, which are used to indicate a partial charge. So this little squiggly looking D, that's the Greek letter delta, lowercase delta, which is really like the great-great-great-grandfather for the D that we use in our language today. Okay? And so what they're saying is this has a positive delta charge of 1, this one has 1, and then the oxygen has 2. Attractions among nonpolar molecules are weaker than attractions among polar molecules, but they do exist. In other words, water has surface tension. Have you ever noticed that? When you belly flop on the water, it hurts because of the strong attraction between the water molecules. Okay? Among the nonpolar molecules, explain why the carbon dioxide can exist as dry ice and why nitrogen can be stored as a liquid at low temperatures. I'm sorry, I said that wrong. Oh, maybe I did. What they're saying is that nonpolar molecules, it's much easier to store them in these conditions. In other words, you could take carbon dioxide, which is nonpolar, and make dry ice with it, and it could be stored as dry ice. You could take nitrogen, which is nonpolar, diatomic, and you could save it at a very low temperature and not have to worry about how it interacts with things. Okay? That's all I got for today. Do you guys have any questions? All right, so what I would like for you guys